questions on projects? Anything like that? Okay. I want to give you guys one example. This is what I was doing last night, in case anybody wonders what did I do for fun. This is it's a surface, it's a remapping of a bunch of thermodynamic data. But I wanted to show you guys because I looked at this and there's going to have to be a lot of optimization going on here. Do you guys think that this is a good function to optimize or not? And why? Why? Ooh, how many minima does it have? You sure?
Oh,
It is, in fact, convex. No, it's not convex function, but it is only one minimum. It's only global minimum. Anybody else see any problems with it? Think about what's going to happen if I throw this guy into a gradient descent, and it's over here. These guys just continue out flat at basically zero, right? So this is flat, that's flat, that's flat. What do you think is going to happen if I sample a part that's flat? Good initial guess is always needed. Anybody else? Come on, guys. Thought we were studying here. You have curve that looks like this, right? First of all, how do you find the root of a nonlinear curve, right? Or an optimal? Somebody tell me here. Right, root finder. Okay, root finder is one way. For an optimizer, what would you do? Same kind of idea, same person's name, just without the co-author. Root finder would be Newton-Raphson, right? Optimizer would just be Newton, right? And what you're doing is you're just kind of going downhill. So every point that you guess, you're going to calculate your downhill, right? And you're going to do one of those guys, right? And you're going to go down there, and you're going to find that, and you're going to zero out on your minimum here. What do you think happens if I go up here? I go off to infinity. Big problem, right? Root finders, optimizers, anything that's working off the gradient, flat is dangerous, right? Because as soon as you're flat, you project off to infinity. If you're actually flat, then you project exactly to infinity, right? You don't want that. So over here, we're at flat here, problem. But you see the other problem? Yeah. That would be one option. What's the problem with Needler-Mead? Benefit of Needler-Mead. Yes, come on. Okay. Doesn't calculate the gradient. Super robust. What's the problem with Needler-Mead? Now you guys. I mean, answer. What's the problem with Needler-Mead? See amoeba one. Fast, slow, very slow, right? Because Needler-Mead, you're just kind of walking through everything. So, you're a TA. You three. What's the other problem with this guy? So we've covered this region. If I start out here, I'm just going to project to infinity, right? That's a problem. What if I'm somewhere in here? These guys are basically valleys.
you just get dropped out without finding it.
Yes, but why? So the valley floor actually does go downhill. Very, very slightly, but it does. I just kind of have to take my word on that. It does decrease very, very slightly. So you won't get stuck analytically. Anybody else? Are valleys good or bad with optimizers, with anything gradient? And why? They're bad. Why? Relative error. It's related to that. Part marks. Relative error in what?
Too high that it would stop it now.
Kind of. What's the benefit of conjugate gradient versus GM res? Do you guys remember what the problem was when we started talking about iterative methods? We talked a lot about values. What happens if I am here? First of all, where's my gradient? Kind of like this, right? So it does have a component towards the minimum. That's fair. But the majority of the component is where? It's going down, right? So what's going to happen with my path? That's a killer. Yeah. Yeah. What's going to happen is, where would this be? I think it's actually under iterative linear solvers. It's better go back and hit the books. Come on. Where would this be? Nomenclature. I thought it had some, it's probably this guy. It's this. Right? So what's going to happen is that when it's over here, you are going to have a little bit of a component. So you are going to move towards your minimum. But your main component, your main gradient component is going to be that way. You're almost always going to overshoot. So now you're up here. And now you're going to overshoot the other way. And now you're going to overshoot the other way. And you're just going to keep doing this guy all the way down. And it's going to take forever because you've got the taco. Right? You've got a taco and your optimizer, your path is just kind of doing this. It's slowly making progress. But what you're going to see is your problem is going to advance. Your solution is going to get better, but you just keep undoing the previous step. You just keep going like that. Final question, and then I let this one go. What could be a nice warning sign? What would I have to calculate if I was here in this area that would warn me that I have this problem? And actually, there is a connection to today. That's good. Okay. I just realized there is actually a connection. And it's a connection that I warned you guys about like 10 weeks ago. The eigenvalues, yes. What do you think are going to be with those eigenvalues? It's literally the name of the lesson today. What about the eigenvalues for this? This is the connection. It's great. It actually works. Do you guys remember what eigenvalues are for surfaces like this? So the eigenvalues for surfaces like this are your main curvatures, right? We'll see why. I have some nice examples. So with this one, what do I do with my chalk? You're going to have one eigenvector is going to be in your main curvature, which is your up and down like that. That's going to be super high because you have massive curvature. And the other one is super small because you're basically going straight. So you have a large eigenvalue and a small eigenvalue. Anybody remember what measure I'm using that relates to this? The condition number. Condition number is the ratio of max to min eigenvalues. So for something like this, you're going to have a massive condition number. And what's going to happen, right? Condition number relates to the stability of the algorithm. So what's going to be happening is your dominant eigenvalue is your big curvature. That's going to be the thing that's having the most effect on your iterative update, to the point where, Ethan, connecting back to what you were saying, right? Any change in your smallest direction, which is that one, which is the one that you actually want to progress is, gets washed out by the numerical error, right? You're too busy worrying about the big curve to see the small curve, which sucks because you don't actually care about the big curve. You actually need the small curve. So this is actually a terrible one to optimize. But at least it does have a local minimum, and at least this doesn't like go off to infinity or NaN on the other side, which is surprisingly big draw. Okay. So apart from you guys needing to go back and hit the books, let's move on to eigenvalue problems. All right. The problem, a big problem with numerical methods is going to be that it will give you an answer to a specific problem, but in very few cases will it give you some kind of like general information with this stuff. So an example, if you got assignment 5, I think it was question 2, you weren't given alpha and A, right? So if you non-dimensionalized, if you did the coordinate transform, that was the correct answer, by the way. You coordinate transform your x and t to remove alpha and A. And then you get, and I think the transformation was what? X, we'll take it up on Monday. X over A, t tilde comes out to t, I think it's alpha over A squared, right? So if you do that coordinate transformation, you eliminate A and alpha, and now you just have your new coordinates x tilde and t tilde, right? And when you solve that, you get a solution in terms of x tilde and t tilde, which are valid regardless of A and alpha, right? They are independent of your parameters, which is an example, a single example of using numerical methods to find the general solution, as opposed to assuming a value, grinding it through, and then only finding a specific value, right? In basically every single case that I've seen in 20 years, there is very little value placed on specific solutions. They almost always want a general solution that is super easy to evaluate, to the sacrifice of a whole bunch of other stuff. Nuclear is really bad for that. I won't say really bad for that. Nuclear really favors that, because like if you can get a one-dimensional solution of something that evaluates like that, you can calculate analytically. A lot of people don't really care if your error is plus or minus 30%, which is a huge error. But honestly, if you can show that, if you can validate that over a range of conditions, burnups, temperatures, years, blah, 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 right? They will favor that over super sophisticated, multi-scale, multi-physics, high-performance computing, exascale, petaflop, neural net, GPU, TPU, because nobody can run that thing. And when you do finally run that, you get a single answer, which is still 20 or 30% wrong. You know, maybe you gain like 5%. So you're only 25% wrong, right? As opposed to that solution. It's another good one. Oh yeah, so I've got another story. My postdoc when I was in Germany was with a fellow named Paul Van Uffelen, who's he is the code holder for the Trans-Uranus fuel performance code. And I had done my PhD. We were doing in COMSOL, COMSOL, 3-dimensional, multi-physics, multi-scale, all this beautiful stuff, analytic, Jacobian, blah, 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 blah. Paul's Trans-Uranus is 1.5 dimensions. So what he does is he'll take a cylindrical fuel pellet, do a radial 1D model in temperature, and then do that kind of like 2 or 3 times through the pellet, and then have some kind of loose coupling. So they call it 1.5D because it's actually like three 1D codes that are kind of loosely coupled together. So INL at that point, Idaho National Labs, was just coming out with their Moose platform. And Moose is kind of like built to take advantage of their high performance computing, right? So they were off on these workshops and things. And they showed an example of a US fuel rod, which is 400 pellets. Okay. So these things are like meters long. You've got one pellet is this. They had 400 of these guys stacked, modeled in full 3D, right? Heat transport, mass transport, structural mechanics. You've got your pellets impacting the clad. The clad is kind of compressing, but not really because it's US. You get the bamboo, you get swelling, all this other stuff. But everything is kind of driven by like the temperature in the fuel pellet, right? And Paul leans over to me and he says, what is that? You know, very impressive. I think this thing ran on like 2 or 3 million cores, right? Using their massive leadership scale, flagship computing, whatever. And Paul leans over and he says, what is the value of this when you don't know your thermal conductivity to within 10%? And it's kind of true, right? Like their whole point with this 400 pellet thing was, what if there was a manufacturing defect and one of the pellets was slightly broken, so it had a sharp point that kind of impacted the cladding? Would it cause a cladding failure? Which is fun in a great examination. But when push comes to shove and industry gets involved, do they really care about that? Because your uncertainties on that are just massive. In which case, why not go for the simple one that gives you the general solution that you can just grind through super quickly? Anyway. There is a lot of value to computational multiphysics and multiscale and things like that, but I think people tend to get carried away. And I have a great term, but I can't share it with you, not while I'm being recorded. So if you're curious about what Paul calls that sort of thing, come find me after class. I think there is a lot of value to it, but you kind of have to keep in mind at the end of the day, like what's actually practical. Okay, so what is actually practical? Let's get to the point, right? The general solutions are the practical ones. The simple ones are the practical ones. The problem is that when you have a great big complicated thing, how do you like boil that down to something that is simple to actually do, right? In computational multiphysics, we actually figured that one out a little bit when we were talking about eigenfunctions there. So if you guys remember, we had that, I think it was the bottle, the Helmholtz resonator, we blew across the top of the bottle, right? And we did all this COMSOL, like, I think, what do they call it? Eigenmode expansions. And I'm sure all of you guys completely understood it then, backwards and forwards. But just in case anybody needs a review, the whole point was that you find the eigenmodes of your system, only linear. It only works for linear systems. And you find your solution in terms of your eigenmodes. And those eigenmodes are your natural basis for these types of physics. So for the what's a good example? Any kind of signal, right? Any kind of, you guys are all over signals and circuits, right? Any kind of harmonic signal. What is the natural basis for harmonic signals? Sine and cosine, right? Because sine and cosine are, first of all, complete. Every single signal can be represented in terms of sines and cosines, but they're also orthogonal, right? So if you integrate over a sine and a higher frequency sine, you will always get 0 unless those frequencies are matched, right? So it's a what do they call it? A complete orthogonal basis for this stuff. But you see the power of this thing. I'll show you guys the power of Fourier, right? Like you put it into Fourier and all of a sudden all the complex physics falls apart and you just get like a couple points on the graph, right? That's the power of the eigenfrequencies. With the Helmholtz resonator, we found those eigenmodes and then we just kind of mix and match them, and all that changed was the relative amplitude of these guys. The shape didn't change. All that changed was the amplitude. That's super powerful because now you can do, there's a group in Clarkson in the US. It's called proper orthogonal decomposition. It's one of these reduction of order modes. No, reduction of order models, ROMs, right? and they take this massive complicated thing, work out your eigenvectors, and then just replace this million DOFs model, three-dimensional, whatever, with like two equations. And those two equations they're data-driven. They are like 10% accurate, and they capture everything. Their application is heat transport on a microchip, on a GPU microchip. And do you shift the load between your GPUs in order to make the whole thing temperature like kind of balanced? You don't want to be simulating the temperature over the whole thing because that's going to take more process than it's worth, right? But you do those in two equations, and all of a sudden you get really good performance. Okay, how do we do this? Eigenvalue problems. Did you guys cover eigenvalue problems in linear algebra? Is that in first year? Okay. All right, so we're back to our linear system, right? We've got our matrix A. Sorry again about the formatting. Oh, I'm just going to jump over to Colab. Okay. We've got our matrix, our vector, and then lambda and that vector, right? Lambda is the eigenvalue and it's a scalar. A is some matrix, right? And then we've got our eigenvector, which is x. Anybody know what eigen means, by the way? You should. Anybody else? Eigen means one. German. Right? Because it is a one vector. It is a transformation that goes to itself, just being scaled by something else. Okay? So what the eigenvectors do for our case, because we feeble engineers, right? Like we need to picture these things. Speaking for myself, obviously. Right? With these sorts of transformations, A is a linear transformation, right? You take some vector and you transform it to some other vector. What the eigenvectors are doing, what the eigen transform is doing is it's saying that in that transformation, there are special vectors that only get scaled, right? Everything else about them is the same. I'm just going to point to 3 blue, 1 brown. They have a great video on this. Super useful. But I will show you. And again, you just click on the rocket ship and launch the Colab to get this. So this is a circle that's just like kind of a general transformation. So starting off on the unit circle, right? We can change this to, oops. So this is just A, B, C, D is just the components of the matrix here. I don't know why that's only one there, right? If you do that guy, it's going to increase like that, but that hasn't changed your eigenvectors, right? All you've done is like scale up one and scale over the other side. These are still your eigenvectors because these guys have only changed in their scale. These guys are not because they've actually moved. They've moved from here to here. That would be useful to show some arrows, actually. I'll make a note of that one. But when you do something like that, and now your matrix is not symmetric, all of a sudden, first of all, your eigenvectors are no longer orthogonal, and it's no longer obvious, right? Like this is not one of the semi-major axes. It's not just a simple stretch in one dimension. If you make it symmetric again, then you get it back to the semi-major and semi-minor axis. Okay? And notice also that these guys are starting to rotate around, right? So this is really kind of getting a little bit messy how you do it, but it becomes a lot easier for symmetric matrices. For symmetric matrices, that transformation is the Hessian, the second derivative of a surface. So you can have some surface, f of x is equal to like some quadratic. Take the second derivative and you will get A. You will get that matrix. So I really like that one because now I can actually visualize this thing, although it's not in Plotly. So I can't rotate it. This is basically how I understood eigenvectors and eigenvalues in my limited way anyway, right? So what you're doing when you do this, you're increasing your diagonals, and we get to, what shape is that? It's parabolic. Actually, all of it is parabolic because it has the second derivative is constant. Yeah. This is the taco, right? This is exactly the case where you're going to have, I should have this outputting eigenvectors too, eigenvalues. So your eigenvectors are actually still 1, 0, and 0, 1, right? The stretch associated with this transform is 9. So that's actually going to be our eigenvalue, right? This is a super simple matrix. It's just diagonal. For diagonal matrices, your eigenvalues are just the value on the diagonal. So this guy, the major eigenvalue is going to be 9, which is big, right? We can make it bigger. And the smallest one is going to be 1. And we have the taco problem, right? Because we have a massive, massive gradient going like that and almost nothing at all going down here. And this is still quadratic, right? So that is actually a minimum here. And it is a quadratic minimum. So Newton's method should solve for a quadratic potential. Newton solves in 1, right? So it will solve in 1 if and only if the numerics don't hide it in the finite precision. So when you actually get out to this, it could just fail entirely, even though it's quadratic, which is super annoying. If you do, so now we're changing B and C together. And what happens is your entire thing starts to rotate, right? So just by doing that, sorry, not rotate, it skews. So as you, oops. As you start to increase your diagonals, first of all, your eigenvectors naturally go this way because this is the way that you're stretching it out now on that diagonal. And you can see on your surface, it stretches it out in one way, not the other way. And if you keep increasing your diagonal values, not only does my code crash, but you also end up with, actually, I think that's gone saddle point, hasn't it? Yeah, look at that. Now we're even in a saddle point problem. Right? You've got curvature going one way. You've got the curvature going the other way. Is this going to work in a normal minimizer? Would this work for Needler-Mead? This is total comprehension question, guys. I just submitted the final exam yesterday. Is this going to work for Needler-Mead? No, because it's just going to fall right off the edge, right? So is there an optimum for this figure? There is, but it's not a minimum or a maximum. It's an extremum. It is an inflection point because you've got one dimension, positive curvature, and the other dimension, negative curvature. So you need something that is gradient based, like Newton method, in order to find this one. Are these ones common in reality? Right? Especially for constrained optimization, they are quite literally everywhere. Okay. In general, eigenvalues are actually super easy to find. We're going to see why and actually use it probably like 100 times a day because it underpins Google. I think somebody asked to do PageRank for their research project. Is it somebody in the class? Yeah. So I'll come to that one. Eigenvectors. Guess how you're going to find eigenvectors? So I'm going to find an eigenvalue. I'm going to find a lambda, and that will be the correct eigenvalue. There's no problem with that. How do you think we're going to find the eigenvector? Oh, I don't have my meme on the book. All right. Think back to the book, the original meme where it's like it's all linear systems, and then it's like the dumb guy and like the Jedi guy, right? It's a linear system, right? All we're going to do is plug in one of the lambdas, shove everything on one side, and you're going to get matrix vector equals 0. Does it matter that 0 is your right-hand side? No, it's a linear system, and we're going to solve for a vector. That's how it works. When we solve, do we like to solve linear systems? No, they're terrible, right? Especially because these guys are typically dense. It takes a long time to solve these things. Don't solve it if you don't have to. But if you do have to, at least you have the tools. All right, eigenfunctions. Running a little bit behind. What on earth is the connection between eigenvectors of a matrix, right? So here it is, right? You've got eigenvalues, eigenvectors, which are apparently some property of a matrix. And then I'm going to say that it's tied into heat transport, right? Time-dependent heat transport. Somebody tell me that connection. Which is also kind of the entire point of the course. Anybody? If I gave you a linear heat transport problem, right? Linear partial differential equation that describes heat transport, and I told you to solve it, what would you do? Guys, this is like legit on the final stuff. What's a good go-to method to solve it? Say 2-dimensional. I'm going to go row by row. Back row. How do you solve it? Throw something out. Crank-Nicholson. What does Crank-Nicholson do? Crank-Nicholson will help you with which part of it? Ready for the steal? Crank-Nicholson is a time-stepping method. So that'll help you with the time stepper. That's part of it. Yes. Okay. I'm going to come back to you later because you threw out Crank-Nicholson. One for the steal. Finite element. You could do finite element. Yeah, that's fine. If you were going to do it in hand in class, you won't have to do it by hand in class, by the way. But if you were going to do it by hand in class, you wouldn't use finite element. You would probably use finite difference. But it doesn't really matter. Okay. When you do all that, what are you going to get out at the other side? What is the entire point of all this? Ready answer. Next row from the back. Dell computer with a bunch of stickers. So I start off with some differential equation. It looks like okay. We're going to throw Crank-Nicholson on this one. I'm just going to cheat and say backward Euler. That's easier to write out. Okay. So this guy, I know my temperature at every point. I know my previous temperature at every point. What do I do with this guy? What happens to it? When we do finite element, when we do finite difference, what happens to this? Does it stay as like weirdo symbolic something that we have to put through Mathematica? No. What does it get changed into? A matrix, right? That's exactly right. So you put this through FEM based on integration, Gaussian quadrature, blah, 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 blah. You're going to get some kind of matrix that has some, beautiful sparsity pattern, but hallelujah, at least it's sparse and it's kind of technically different, right? If you put it into finite difference, then you're probably going to get some other matrix which has some kind of banded structure in 2D, but it doesn't matter. It is a matrix. right? The matrix is the tie-over with the eigenvalues. The eigenvectors of this matrix and the eigenvalues of this matrix are exactly the eigenvectors, functions, of the problem that you are describing. So if I want to go back here and say, like, what are the eigenfunctions of heat transport? I could completely legit do this, do finite difference, do finite element to get to a matrix. Find the eigenvectors, values of that matrix, and those are precisely that. Okay? So we take our unknown field, we represent it as a vector, we write our differential operator, our PDE, as a matrix, right? And then we do some kind of vector function, right? For a nonlinear case. For a linear case, we just do like the normal, like just AX is equal to B, right? For the nonlinear case, we'd have to throw that in a root finder. Problem with the root finder is that A updates on every iteration, but that's still how you get it, okay? What we're actually doing is writing this in, we're writing our field, our temperature field, in terms of a linear basis, right? Some combination of functions that are easy to work with. If we had an infinite basis, right? So if we had finite element method with our elements super small or very high order polynomial, if we were doing finite difference and we had super small time spatial steps, right? We would have the exact solution, right? I learned about that with Brockett notation with quantum, right? They were talking about like infinite bases and oh my god, right? We're not going to go there, right? But it's all tied together, okay? What this means, so consider you did this, you found the eigenvectors and the eigenvalues. Yeah? If you then looked at those eigenvectors, which represents a function, what would happen over time? Right? Your time stepper is taking the previous one and changing it into something new based on this differential equation, based on your operator, your linear operator, which is a differential equation, okay? What happens is your time step plays with the relative magnitudes of your eigenfunctions. Okay? Your rate of change is related to this differential operator of your unknown vector, right? So you've got some matrix, you've got some vector that represents your temperature unknown field. But this guy can just be expressed in terms of some combination of eigenvectors, which means your rate of change just plays around with the magnitude of these guys. That's why for the Helmholtz operator, all that we had to do, we had to find the eigenmodes. That was finding these vectors. And then all the solver had to do was update the relative magnitudes. That's it. That's the magic of this stuff. It sounds weird. It sounds freaky. You guys all know how to do this already. Your body already knows how to do it. I think my daughter learned when she was 3 how to do it. Anybody ever sat on a swing? Right? What do you do if you want to go higher on a swing? Right? You move at what frequency? First of all, pop quiz. Resonant frequency. What does that mean? Why? Right? So here's the magic, right? Does your frequency on the swing depend on your amplitude? No. Right? No matter how high you start on the swing, you're still going to go backwards and forwards in the same amount of time. It's just not the amplitude, right? Your amplitude of oscillation is going to change, not the oscillation itself, because of the small angle formula, which is only valid under certain approximations, blah, blah, blah. We just talked about the approximations, right? That's a quintessential example, simple harmonic oscillator. If you want to go higher, right? Higher means increase the amplitude. It doesn't mean change the frequency. So to have resonance, you need to pump your feet, your forcing function at the same frequency as the natural frequency for that thing. And then, and only then, do you actually go higher, right? If you are, who was doing the musical instrument for Eigenvalues? That was you guys, right? Yeah, right? Like if you just take like a flute or a recorder and you just blow into this thing as hard as you can, right? It's going to sound awful, right? Because you're not at the natural frequency. There is, next time you're on a swing set, try it. There is a second resonance. It actually, there's a whole continuum of resonances. Nobody ever hits it, but if you try and like double count, so get your rhythm for that and start to pump your feet at like these like twice per rhythm, what you're going to do is one of these guys, right? And there is actually a stable mode there too, right? You can get to it. It's super awkward, right? Everybody wants the fundamental frequency. The fundamental one is the lowest one. So all of your what ends up happening is that you scatter off the energy, and it kind of goes down to the lower the fundamental mode. That's kind of what it happens there. All right. I'm just going to quickly show you guys a coupled oscillator. So this is a super simple one. It's just like two mass objects on a spring. The spring is connected to each other. So the acceleration is related to the distance of one from the wall and then the distance between the other two, right? In vector form, what we would do is we would say the unknown vector is just our positions, right? And we can just write off our acceleration. Super easy, like that. And this is just an initial value problem. So we will go through, got to launch it in Colab again. Run all, and then I'll let you guys go. So this looks terrible. This is an example where you would start one mass object like kind of farther along. The other one is at 0. Doesn't work very well, but it still does form some kind of harmonic basis, right? And if you go a bit lower, you can see, okay, this is your eigenfrequency. This is your Fourier spectrum. There is magic, though, when you start off your objects. Should have at least a picture showing you guys what this is, right? If you start them at the same position, then it's like starting a Newton cradle where both of the balls are kind of in the same spot. All they're going to do is this. Still simple harmonic motion, but everything just kind of stays in sync. If you instead, right? Ugly, 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 ugly. And all of a sudden, you get this, right? And this guy is something that's doing one of these guys. Back and forth and back and forth. Okay? We've gone from something that's ugly into something that is beautiful. Guess what? 1 and 1 and 1 and -1 are going to be. They're going to be our eigenvalues. Okay? So, all this to say, don't get hung up on the math. We already know eigenmodes. Whenever we walk, right? Walking is controlled falling. That's all about eigenmodes. And whenever we do anything with resonance, whenever we're talking, is all eigenmodes. The way that we distinguish one pitch, one sound from another one, is the eigenfrequencies from sound waves going into our head. We understand how this works, but the math kind of gets in the way, to be honest. But we'll talk about it more Thursday.
Okay. Let's take this thing home. Okay, so we were talking about eigenvectors, we were talking about eigenfunctions and values. As a reminder, the idea is that what we've learned how to do in this course, especially the second part of the year, is to take our differential equations and put it into a vector equation, right? So we take our diffie-q's, we put them into some kind of algebraic equation. If it's linear, it becomes a linear system of equations, and we're back to like the first lecture of the class, right? When it is linear, and even when it's nonlinear, the idea with the nonlinear is to make it linear and then solve that as an iteration, right? As soon as you get a linear form, you can talk about these eigenfunctions, eigenvalues. If you don't remember what they are, I don't blame you. They are the natural form of these matrices. So matrices in general will transform one vector into another vector. The eigenvectors are the special ones that get transformed to themselves and just scaled, right? That's kind of the best way that I can describe it. But what that means for our partial differential equations in particular is that it's going to take certain parts of the physics, and when we time step it, because time stepping is just taking like, hey, what is our current solution, which is a vector, transformed into our next solution, which is another vector. Certain components of those vectors are only going to be scaled. And if we know what our vector is, what our total solution is, in terms of those magic components, then the math becomes super easy, right? That's what we were talking about with the module in COMSOL last year. That's what we're trying to nail home today. Okay. This is just going to be a quick review. This has nothing to do with numerical methods. It's just how we would normally find the eigenvalues of these matrices, right? So this was the coupled harmonic oscillator. We finally got the book working again, by the way. Okay, this part is about numerical methods, and more importantly about computational multiphysics and just computers in general. Have you ever wondered, are you guys aware that like most of like nuclear technology operates with like Fortran code? And not even like Fortran 77, like Fortran, the original Fortran. You ever wonder why like legacy is such a big thing? The Jupyter book was working, this thing was working last year. It was working absolutely fine. And then we go and update something and try and rebuild it. And the way it works is that we edit the code, GitHub Actions takes it, puts it together, and like puts it up on the page. All of a sudden started breaking and started going back like 4 months. And the error codes that we got, right? Error codes are great for this, right? Completely misleading. We're saying it's something to do with this, and it's something to do with this, and it's something to do with this. Meanwhile, one of the codes that had updated in the background was incompatible with another one. And that just an incompatibility wasn't like obvious. And that was the cause of the problem. So my student Mateo had been hammering away at this thing, trying to rebuild everything, nailing down everything, like taking it apart piece by piece by piece. And all the while it was because we couldn't use like the latest version of whatever under code in the background somewhere. Like this is why nobody wants to update their computers. Like, honestly, that's just, if you're doing something like banking, if you've ever looked at like a banker's computer, they're running a DOS emulator and running something on like green text DOS. It looks like the Matrix, but not as cool. Like, but this is why, because otherwise something stupid is going to break. Anyway. Coupled oscillators. We get an equation like this. Yeah, let's do it this way. Okay, so we get this equation, right? So this is mass times acceleration is equal to, and then we have springs. We have a spring on one side. We have a spring between our two masses, and we have another spring on the other one, right? And now we're going to solve this differential equation. Last class, we went through this example. I kind of showed you guys. I still don't think this is working quite right. No, right? But I showed you what the paths look like. At least that interactivity is still there. Okay, so the way that you might do it, and you would normally do it kind of algebraically, human-wise, is you're going to assume that your solution is of this form, right? Because you are a harmonic oscillator, you're going to use a harmonic solution, which means you're assuming x is e to the negative I omega t, right? And now you're doing this harmonic motion. And the nice thing is that your acceleration just turns out to be negative omega squared times this exponential. Oh, I heard a couple days ago that nobody can actually read this text, so I'm going to try and make it bigger. Is this legible for guys in the back? Yeah, okay. Okay. When you plop this guy in, you say that you take your x1 and x2, you make it into a vector, right? You get all these funny guys. And note that what you have now is going to be a linear system. You've got an x on one side, you've got an x on the other side, you've got another one here. We're going to group terms. Okay? The solutions to the equation is either going to be trivial, x is equal to 0. You place them, right? They're not moving anywhere. They are exactly balanced. Nothing interesting happens. There's no time dependence. Or it could be non-singular if and only if the matrix is singular, right? Why do we say singular? Because it has to have null space of 0. It has to map exactly to 0. Okay? When the matrix has to be 0, then we know that if we have these eigenvalues, if we have these constants here, I don't know why I didn't rearrange that stuff. All right. You've got a function over here, big matrix over here. You're going to group these terms, and you're going to set that as equal to 0. And if we're going to do this, we're going to find this matrix. What we need to say is that the determinant is 0. Right? That's the criteria for a singular matrix. These magic values are your eigenvalues, and the corresponding x is your eigenvector. Right? And what that works out to be, I don't know why it didn't. Oh, you know why? Hold on a second. I think this is that funny line thing. Yeah. Again, legacy systems. Here we go. That's better. Okay. Make that bigger too. So we're assuming a function of this form. We plop it in here. We get something nice. Put it into our equation and rearrange. And now we get the matrix equation. Okay. Sorry, sometimes the line return doesn't work right. Okay, so either x can be 0 or x can be non-zero, in which case this has to map to 0. And the only way that's going to happen is if this is singular, right? So this is a matrix times some scalar identity, and we're demanding that the determinant be 0. Got to make it a little bit smaller here. And in this example, our eigenvalues for this, right? This is our matrix. This is our scalar. So this scalar is the eigenvalues. They're going to be 2 because it's a 2 by 2 matrix, right? We've grouped them, which is nice. So we can say that we've only got like kind of one parameter because everything else is kind of grouped inside there. And the nice thing about determinant is that it's a polynomial. So when you do the determinant, I don't think I wrote out the, oh yeah, no, I did get the polynomial, right? So this is your determinant, turns into lambda squared minus 4 lambda plus 3. Find the coefficients, okay, that's not so useful. And the nice thing about that, so the roots of this polynomial are going to be our eigenvalues, right? That's what lambda is going to be equal to. How do we find the roots of a polynomial? You guys are brutal. Do you guys remember finding roots of a polynomial? Do you guys remember finding roots? All right, that's good. Do you remember finding roots of a polynomial? Just do you remember at least finding the roots of the polynomial? Does anybody remember how we found the roots of the polynomial? We could use an analytical solution, right? In general, that's not going to work because if your polynomial is, I think, above 5, order 5, there is no analytical solution. So below 5, yes. For a quadratic, yes, okay. You can just find it analytically, right? But in general, we want to use this root finding method. If and when you go back into your notes, obviously, right? What you're going to find is that finding the roots of a polynomial actually amounts to finding the eigenvalues of a companion matrix, which obviously isn't the right answer. Right? We haven't found a matrix. We're going to find the roots, and we're going to find that using an eigenvalue algorithm. We're just doing circular logic here. But we can still use it as an example, and then I'll show you guys how it's actually done. Right? So the eigenvalues turn out to be 3 and 1. In order to find, how do you think we're going to find the eigenvectors? Now that we know our eigenvalues, this is a real question. I'm not letting this one go. How are we going to find our eigenvector? So what we know over k is equal to 3 and 1. I can barely see that, huh? All right. We know what this group of terms is. It's either 3 or it's 1. We found that out. How are we going to find our eigenvector? Don't say analytically. What's that? No, we've already found the eigenvalues. So the companion matrix will give you the roots of the polynomial, which are the eigenvalues. So that's going to give you this group of terms. But now we're going to plop this in 3. And how are we going to find x? Eigen decomposition. No. LU decomposition. All it is a matrix equation. That's all you've got. We're right back to the first class of the lecture, right? All you've got is a matrix, any matrix, times a vector is equal to a constant. The constant just happens to be 0, right? 0 is a constant, b is 0, and you've just got ax is equal to b, right? And you're just solving for x. That's all you're doing. Is it easy in general to solve for x? Right? As soon as you do that, you're into linear systems. They can be expensive, right? So yes, we know how to do that, right? Yes, the correct answer is LU decomposition, absolutely. But yeah, that's all we have to do. When we put that in, right, we can just throw this into either a root finder or just solve the linear system since one is a subset of the other one, right? And what we're going to get are 2 harmonics, 2 solutions. Either x1 is equal to x2, which was the case that we found where both of these guys were oscillating together, or they're exactly opposite, and they're going to do this accordion thing. Yeah. Okay, so this works because our matrix was small, is only 2 by 2, right? And therefore, we could throw like analytical methods at it. But in general, we're going to have much larger matrices. So how are we actually going to do that? I think I asked this last class, but there was somebody wanted to do the PageRank algorithm from Google as their design project. Are they in the room now? Oh yeah. So what we've seen is that a linear system will transform one vector onto another one, right? The magnitude of that scaling along that magic vector is our eigenvalue. What Power's method does, it's aptly named, actually. Basically, you're going to take a random vector. Doesn't actually matter what vector you're going to do. And that random vector, you're just going to apply your matrix to it. And the components of that vector are going to be multiplied by whatever the value is in that direction. Okay? The one that it's scaled most by, so the most growth from that vector is going to be in your dominant eigenvalue. So what Power's method is going to do is it's just going to take any vector and just keep applying that matrix and watching that vector as it grows more and more and more in one direction. And as you keep applying to it, it's going to actually nail down what your dominant eigenvector is. So you choose a random vector, you apply A, you normalize it so it doesn't get too big, and then you just keep going. And you go and you go and go. And because it's going to stretch out that vector the most in the component of the dominant eigenvalue, it's going to get bigger and bigger and bigger. Have an example. No. Okay, whatever. Does anybody, oh yeah, so does anybody know what the downsides are? What? Yes, Python, obviously. Okay, so what we're going to do is we're going to take a vector, any old vector, and we're just going to apply this matrix again and again and again and again and again and again and again. Flat out multiplication. Every time after we multiply it, we get a new vector. We're going to normalize it so it doesn't go off to infinity. And then we're just going to keep doing that and doing it. I can't even, but I'm going to zoom in a bit and then scroll up. There we go. All right. Anybody know what the pitfalls of this are? When you multiply, so it's matrix addition, right? Matrix vector multiplication. When you multiply two numbers, okay, this actually is like the first lecture from this class. When you multiply two numbers, are you going to get the correct answer? In general, two floats. Not integers, floats. What's that? Round off error, right? So you multiply two things, you're going to get round off error. And then you multiply it by again. What's going to happen to your error? And it's just going to grow. It's just going to grow and grow and grow and grow and grow, right? So as soon as, and there's no control over that, right? Some of these, the whole way that the implicit solvers worked is that those errors didn't propagate. Those errors damped instead of growing. But there's nothing for it here, right? All you're doing is just making something worse and worse and worse and worse and worse. Also, matrix vector products are not actually so easy, right? Because for every time, if you have a 2x2 matrix, right? But the way that you calculate that is you go row. So 1, 2, add that up. 3, 4, add that up. So it's n squared, right? If you have 2x2, not so bad. 100 by 100, you start to get worse, right? Matrix vector products are not actually so fast, which is another problem. They're also kind of slow. Nonetheless, it is a weapon of choice for whenever you would want to find the dominant eigenvalue. Guess when you would want to find the dominant eigenvalue. And there should be a research talk on this one, I guess, in the next week or so. Anybody know a case when you might want to find the dominant eigenvalue of something? Anybody ever used a small tool called Google? That's what it's doing. That's what the PageRank algorithm is doing. That was a revolution that made it so popular. And as I'll leave it to them to talk about. It builds a special matrix, right? And the dominant eigenvalue of that is the answer that's probably most relevant to you, which is really kind of cool because you can imagine how big this matrix is going to be, right? This is the entirety of the internet that it's searching and, you know, it's ridiculously accurate. By the way, so back in my day, when I first got a computer and I did my dial-up modem, we didn't have Google. So we used I think mine was Hotbot or something. And it was so bad. Oh my goodness. And then Google came along and Google was just like a different class of search algorithms. And it was so efficient. Holy hell, compared to the alternatives. It's like using, what do they call it? Not a lookup table, but basic keyword search. It's like Hotbot and all that was built using like keyword AOL search, right? Was all built using keywords. And then Google comes along with this PageRank thing and just holy hell. All right. Let's have an example. Blah, blah, blah. Excuse me. Blah, blah, blah. Feel free to take a look at this. It's pretty simple. All we're going to do is initialize, find a random variable, and then we're just going to keep multiplying it over and over and over and over and over again. And what it looks like, that's just plotting. So take a vector and start multiplying it more and more and more and more and more, and all of a sudden it stops. Right? And this is because whatever, say our eigenvectors were what? Say they were this, we didn't know that from before. I'm gonna make it a bit easier. Can you guys see at the back? Yeah. I did calculus over summer school. That's how I did like high school calculus. And I got one of the best pieces of advice that I've ever gotten in mathematics and science in general. Are you guys ready for this? Always draw your plots as big as you have space for. You will never have a plot that is too big. You will always have a plot that is too small. Transcendent, right? This, right? I have way more space than this. And now like half people can't even see it. And as soon as I start to label anything, then it's all going to get like mussed up and then everything gets scribbled over each other and it's just going to be mad. Always draw your plot as big as you can. There we go. You see that one? There's your dominant. There's your big one. Right? Yeah. Now we're talking. There's our smallest eigenvalue. Eigenvector, right? Any vector here, let's say this guy. Any vector here is going to have components in the eigenvectors. That's how like vector decomposition works, right? So this guy is what? Something like that. And this guy is going to be something like that. And that, I'm drawing that terribly. How's that? Right? This is just the negative. This is just the eigenvalue negative of that vector, right? When you multiply it by some matrix, it's going to make it larger. No, it's going to map it onto a different vector. But whatever this component is going to get magnified. And whatever this component is, this guy is going to get shrunk. And that's just because of the eigenvectors, the eigenvalues along those vectors. So whatever angle you take, you break it down into the components, and it has to align with that vector. And the eigenvalue, they work out the eigenvalue from this. I think you just solve for the eigenvalue. Yep. There you go. So your normalization, once you've got the transformation along that eigenvector, right? Whatever that transform is, whatever the ratio back to the unit is necessarily your eigenvalue. If you want to rerun it, get new random vector. Now we're at something else. It doesn't matter. It's still going to find it. Should have a little button for that. Right? New random seed. Is this a problem? Previously, this vector kept going up here. Is this a problem that now it's pointing down this way? No, right? Because it's just the negative. All we've done is find the negative. The eigenvector, the directionality still hasn't changed. Any idea what we do for the smallest one? Almost. Matrix division. Careful. Almost. Matrix division. Hold on. What is matrix division? Anybody use MATLAB? Like big MATLAB fan, right? Like, do you know what matrix division is? Exactly, right? But you can put in something that looks like matrix division, right? You had to, what's that? Invert it. That's what matrix division is, right? And that's what MATLAB is doing too. MATLAB was my first language, first one that I was actually any good at, right? So what you're doing when you're doing normal division, if you want to say A divided by B, you would say A times 1 over B, right? But if you have, let's say, okay, MA, right? What we would have to do if we, that just makes sense. Whatever. Rows, columns, balancing, all that fun stuff, right? If you wanted to do matrix vector and you want to divide by it, you would be multiplying by 1 over m, otherwise known as the inverse. But 1 over a matrix doesn't really make much sense. Mathematically, what you're talking about is the inverse. And that's all Powell's method has to do that. But now it's a little bit trickier, right? Because now you need to invert the matrix and then reapply that algorithm. So you've got another step on that. Turns out the matrix inversion is roughly equivalent to matrix vector products anyway, in terms of complexity. So you're actually not so bad with that one. Any idea why you would want the lowest eigenvalue? Again, 2x2 matrix only has 2 eigenvalues. Don't worry about that. Any idea why you would want the lowest one? And I think we actually talked about it in 2CM4. The lowest eigenvalue is super, super important. First of all, for condition number, if ever you were wondering about the condition number, blah, blah, blah. The eigenvalue is going to relate to the stability of your system. So when we did the von Neumann stability analysis, we talked about like this error propagation and where the smallest one was, if it was 0 or non-zero. And if we're outside of the range of the smallest eigenvalue, then we don't need to worry about anything. If you guys ever go into structural mechanics or like go and build a building or do anything actually useful, right? Your smallest eigenvalue is going to be the one that's activated first when you have something like an earthquake or wind, for example, right? When the wind hits your building, your bridge at just the right frequency, you're going to get resonance. And that smallest eigenvalue, right, is going to be the smallest frequency of the wind gust that you're going to need to activate that. So it doesn't have to be, you know, like if you have this big typhoon strength, like wind, hurricane, yeah, your bridge is going to fall down, right? But if you have just a teeny tiny little bit of wind, do you really have to worry about that? And it turns out, yes, if you hit a resonance frequency, right? Now you look into the London Bridge, that all of a sudden, like everybody hit the harmonic when they were going like this. The Tacoma Narrows Bridge, you know, it got the aeroelastic frequency and the wind went over the railing just right, so the entire thing shook itself apart, right? This is actually super useful. The way that we would get intermediate eigenvalues is that we're going to remove the ones that we found. It's called matrix deflation. I'm not going to go into the math of why this works. What happens is that you, by taking that eigenvalue, you remove it from the matrix itself through a transformation that looks like that, and this A primed now no longer has that eigenvalue. It's actually a pretty simple transform. And now, when we rerun our powers method, it's going to find a different vector. This happens to be the smallest eigenvalue vector because we're only 2x2. But what we've done is we've removed that big one here. So all we've got, I think what actually happens is that we map it to 0. So we change the eigenvalue of that vector to 0. In which case, all the powers method is going to find still is the only one, is the next largest one, which happens not to be the smallest one because we're only 2. Blah, 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 blah. Okay. Powers method is really good if you want to find the largest or the smallest. Some cases you would want to find all of them. And for that, we don't use any of these methods. We use a decomposition method. I think that's actually my last slide or page. And I'm not going to go into depth on how this stuff works because it's a bit too advanced. The same way that we decompose the matrix into LU to get to a simpler form to be able to solve it, you can also do other decompositions called QR that uses householders. That's going to make it a whole lot easier to find your eigenvalues. So what usually happens when you throw like numpy condition number at the solver, or something like that, what it's going to do behind the scenes is it's going to use these decomposition algorithms to find the set of all eigenvalues, and then just select the largest and the smallest. That's the way it actually works. Has anybody come across the term singular values yet? Singular values, if you look up some of these materials on like Wikipedia and stuff like that, condition number, for example. If you look up condition number, you're probably not going to see eigenvalue and eigenvector, you're going to see singular values. Singular values are a generalization of eigenvalues. In case you didn't think that eigenvalues and eigenvectors were hard enough, singular values are the generalization of that to non-square matrices. So if you have a rectangular matrix, you can't find the determinant, and therefore you don't have a characteristic polynomial, and you can't solve for its roots. Nonetheless, there are still special values, but they are no longer your eigenvectors. They are now your, I forget what they call them, singular vectors and singular values. So that's the generalization. All that uses these decomposition methods because they're more numerically robust. Okay, going through this kind of quickly. So householders is an iterative method. It tries to reduce the matrix to a simpler form while preserving the eigenvectors and eigenvalues. The nice thing about doing that, so what we're going to do is the simpler form is going to be we're going to zero out elements, right? And by zeroing out elements, if there's one element that's zero in your matrix vector product, that's one less matrix product that you need, or one less product that you need, one less source of round-off error, and all of a sudden all your numerics get much more robust just by zeroing out some of those elements. Okay, this is the form. This is how we do the householder reflection. We say that this vector here, yeah, it's similar to another technique, Woodbridge. This is knowing what a particular vector is, one of the eigenvectors is, and we're going to transform out and we're going to zero one of these things. And we're either going to use it to find something called a Hessenberg matrix, which is a simple one to put into a QR code. QR we'll come to in a second. Or for symmetric matrices, it just makes it tridiagonal. And tridiagonal are super efficient for any kind of multiplication, right? We're very simple sparse system. Launch this in Colab. Run all. Okay. So what this code is doing, it's creating a random array, 4x4 matrix, sorry, not array. And then what we're going to do is, oh, that's funny. What's that saying NaN? Wah, wah. Yeah, it's kind of messy. Okay, we're going to have to come back to that one. 1 second. Restart and run all. Wah, wah. Never try and do live demos. All right, well, I'm talking about ending with a bang. What ends up happening is, okay, what should end up happening is that these guys go to 0. Through this reflection, you're effectively eliminating some of those elements, making them 0, and then when you do the matrix product, you don't have to worry about that, that accumulation of round-off error. This is the other problem, because now we've locked back to a previous version of the codes that built it, and apparently they don't have this capability. Okay. QR decomposition. This is why people like PDFs, because you just do it once and then it's fixed and nothing else happens. Okay. QR decomposition. What you do is you get a real square matrix. I don't think it has to be square, actually, for different variants. And you're going to decompose this thing into a matrix, into a product of matrices. One is going to be Q, which is orthogonal, so it has this nice property that the transpose is the inverse. And then R is going to be upper triangular. If A is invertible, so it's non-singular, then the decomposition is unique. And let's see if this guy is going to work right. Yes. All right. Given a matrix, and we should, yeah. So this is our original matrix, right? Just randomly created. Q here is going to be our or orthogonal matrix, and then R is upper triangular. And yes, if you multiply these two together, you recover your original matrix. Otherwise, you can use the NumPy algorithm, which actually does the exact same thing, which is just QR. Real easy. Nice thing about QR is that, so you get this product, you reverse it to create a new iteration, right? Which is just cut off the diagonal components entirely. So it's like householders in that it zeroes out those components, but it does it a bit more efficiently. And then the diagonal just reveals the eigenvalues directly. Okay. Nope, too many iterations here. This is our original matrix. When we go through one iteration, okay, let's keep going. Do you see how these guys are getting smaller and smaller and smaller through the different iterations? Eventually, they're going to hit our cutoff. And way down here, we've got zeros, zeros. And now we've got a nice matrix that has the eigenvalues along the diagonal. Okay. QR, again, is something a bit more advanced, but you guys will probably come at it. And that's what you've actually been using with condition number stuff. Leave. Okay, so I need to go back and clarify this one because that didn't work at all with the new stuff. Any questions?